The condenser is needed in the steam power plant cycle in order to condense the wet, low pressure steam that's leaving the steam turbine back into saturated liquid so that it can be pumped back into the boiler. So let's have a look to see how you might quantify the heat rejected to the surroundings from the condenser. So this is going to be your basic first law analysis of the condenser. And it does turn out that sometimes, depending on what is asked for in the project assignment or problem assignment, you may not need to analyze the condenser. But just for completeness, let's talk very quickly about how you apply the first law for the condenser for a complete thermodynamic analysis. So as a reminder, here's the condenser component. So it's taking, at state 2, it's taking in wet, low pressure steam from the steam turbine. Okay, the condenser is just basically a heat exchanger that's exchanging heat with the surroundings somehow, and we'll show you how that works. And what's coming out at state 3 is a saturated liquid going into the inlet of the feed water pump. And what does that look like on the TS diagram? Well, here I've shown, well, let's see, I've got a couple of states called 2. I've got 2I if the turbine is isentropic, reversible adiabatic, and 2A if the turbine is adiabatic, but irreversible. So one or the other of these is your ingoing state to the condenser. Almost always, it's coming out as saturated liquid. In some cases, some problems in the textbook and the real world, there is some subcooling going on, but let's not delve into that detail right now. You can figure that out if needed. For the time being, let's just say the outlet of the condenser is a saturated liquid. Well, this is a recap of some of the components you've already seen. This is just a picture of that cylindrical vessel that's serving as the condenser. You see there's sort of a kind of a bubble underneath the cylindrical vessel. That's called the hot well, and that's where the condensing steam, which turns into saturated liquid, it collects, and that's where we remove that saturated liquid and send it on to the feed water pump. Continuing the recap, you see in most situations, all the situations I've encountered, there's some type of cooling water supplied to the condenser. That could be river water. It could be return water from a cooling tower. Okay, but in any event, it comes in at around room temperature into the condenser, flows through these tubes, makes a U-turn, flows out, where it has picked up energy by way of heat transfer from the steam into the cooling water. So it's going to leave out a little warmer than it came in. Kind of common sense. Also, as a recap reminder, for most power plant situations, the condenser is operating way below atmospheric pressure. And in fact, nearly total vacuum, so a very high vacuum level. And so I've just given a little example problem of if we're condensing at 20 degrees C, around room temperature, maybe a little cooler, then the pressure inside that saturated mixture vessel is going to be 2.34 kPa. Wow, that is a high vacuum. That's a very low absolute pressure compared to the atmospheric pressure of 101 kPa. Well, what would your sketch look like? So let's think about you solving a problem, either a homework problem or even a real world problem. What would your sketch look like to describe the condenser? I would show it as basically a steady state, steady flow open system. I call it a condenser, certainly showing it as a box, but showing a sort of a squiggly line that indicates heat transfer or tubes going from state 2, the steam state 2 to state 3. So that would sort of convey that you have a heat exchanger going on, and I'm showing Q dot L that's exchanging heat with a low temperature heat reservoir. In this case, that low temperature heat reservoir is the cooling water. Okay. And so let's see, what about some fundamentals? We're going to, for modeling the condenser, we're going to say kinetic energy and potential energy changes are zero from state two to state three. We're going to say we've got steady state, steady flow, open system, one inlet, one outlet. So therefore, m dot 2 equals m dot 3. We'll just call it m dot. The condenser process is a constant pressure process. So P2 equals P3. It's condensing at constant pressure. Let's see, is this condenser lifting a weight? No, I don't see any evidence of that. Is a shaft coming out of this open system? Don't see a shaft rotating coming out. So W dot out for this open system is 0. So we're set up to apply the first law. And so here's our first law that we know we've got this in our heads. Steady state, steady flow, one inlet, one outlet. We've got Q dot in. That's what we're looking for. Minus W dot out. That's 0 equals M dot times H3 minus H2. Outlet minus inlet. And you're going to observe that when you crunch the numbers, H3 is going to be a smaller number than H2. Let's see. You've got wet, high quality steam here. You've got saturated liquid here, X equals 0. And so you know that this is going to be a negative number. H3 minus H2 is going to be less than 0. So that says that the heat transfer into the steam is a negative number. Heat rejected. As a reminder, it's very common that we take this first law and we divide it by m dot. So that in textbook jargon, for the condenser, Q dot in is going to be equal to H3 minus H2, and that's going to be a negative number, just like I've said in my green text box here. Let's see over here. H2 is usually known from the steam turbine analysis, so H2 is usually, it's a known value, no additional work needed there. And H3 is usually saturated liquid, so that's an easy lookup. As long as you know P3, and you know it's saturated liquid, you can go to your pressure table and simply look up H sub F at P3, and that'll be what H3 is. So really, really pretty simple. Now, just to remind you, the condenser is just a basic heat exchanger, is really all it is mechanically. And so if you see that if you take and you draw a control surface around the whole condenser, that includes the cooling water, you'll see that you've got a heat exchanger with 2 inlets and 2 outlets, steady state, steady flow. The 2 streams do not mix. And so this really becomes a fairly simple analysis problem to do. If you're interested in the nuts and bolts, I would chase you to problem 816. And that's where I work through an entire Rankine cycle analysis, and you may be able to get some hints on how you would start and complete your own problem. Well, that pretty much covers it for the condenser. And so you see, all we did with the condenser was just apply the first law of thermodynamics, open system, steady state, steady flow, to solve for the heat transfer. Hope that helps. And let's see, we have one more component to go. That'll be the feed water pump. And that could be the trickiest component to analyze. So please have a look at how you analyze the feed water pump.